Hello everyone. Today's lecture is about work and kinetic energy. So in this chapter we introduce the idea that the force times distance is an important new physical quantity which we refer to as work. And kinetic energy is the energy of motion which is closely related to work. So work and kinetic energy together set the stage for deeper understanding of our physical world. Now let's begin the chapter. These are the learning objectives for today's lecture. And at the end of the lecture, you will learn how to define work and kinetic energy and relate the work done to force. And we will be learning the work energy theorem and also about power. Now this is the chapter outline. We have 4 sections to cover in this chapter related to work and kinetic energy. So what is work? For example, when we push a shopping cart in a store or pull a suitcase through an airport, we do work. We experience that the greater the force, the greater the work, and the greater the distance, the greater the work. So these simple ideas form the basis of our definition of work. Suppose we push a box with a constant force F as shown in this figure. So if we move the box in the direction of F through a displacement of D, then the work done, W, we have done in this case is F times D, force times the displacement. So in this case the force and displacement are in the same direction. Now the units of work is Newton meter. Since force is in Newton and D is in meters, therefore the units of work is Newton meter, or we can call it as joules, J. Now the work is the product of these two magnitudes. Therefore it is a scalar quantity. So keep in mind that work is not a vector quantity, it is a scalar quantity. Now let's find the numerical value of work done for the previous situation. Now suppose you exert a force 82.0 N on the box in the figure and move it in the direction of the force through a distance of 3 meters. Now what is the work you have done? And now in the question we are given the force value and also the distance traveled, and we are asked to find the work done. Now from the equation we know that work done, W, is force times the displacement, Fd. Now in this case the force and the displacement are in the same direction. So we can simply substitute the force and the distance value in the equation to find work. Therefore work is, force is 82.0 newtons and the distance is 3.00 meters. Therefore it is 246 Newton meter, or we can write it as joules. Now let's see one more example. So if you do 5 joules of work to lift a box through a vertical distance of 75 centimeter. Now what is the force you have exerted on this book? Again we can apply the equation for work done, which is W equals Fd. Now this time we have given the work, value of work, and the distance D, and we need to find the force. So now we can isolate force from this equation. Force is simply work done over distance or displacement. So it is 5 joules over 0.750 meter. So we have to convert centimeter to meter, which is divided by 100. So it is 0.750 meters. Therefore the answer is 6.67 and the value is unit is in Newton, because joule is Newton meter and divided by meter get cancelled and the unit is in meter. Let's see one more example. An intern pushes an 87 kilogram patient on an 18 kilogram gurney, producing an acceleration of 0.55 meters per second square. Now we are asked to find the work done by the intern when she pushes the patient and the gurney through a distance of 1.9 meter, assuming it is moving without friction. And in the next part we are asked to find the distance the intern pushed the gurney to do 140 joules of work. Now in this question we are given more parameters. First we are given the mass of the patient and the mass of the gurney and the acceleration. And in the first part we are asked to find the pushing, we are asked to find the work done, but we are given the pushing distance. So we are given the distance and we are asked to find the work done. But in this case we are not given the magnitude of the force F directly. Therefore we have to find the force first in order to find the work done. And in the second part we are asked to find the distance by giving the work. So it is simply W equals FB and we need to find D, which is W over F. So those are the unknown parameters. In part A we need to find work, and in part B we need to find the pushing distance, which is D. Now we can find the force exerted by the intern using the Newton's second law of motion, which is sigma F equals mass times acceleration. So we know the total mass of the system, which is the mass of the patient and mass of the gurney, and we have given the acceleration. Therefore we can substitute the values and find the force. So mass is 87 kilogram plus 18 kilograms times acceleration is 0.55 meters per second square. So if we solve for it, we get 58 newtons. The force is in newtons. Now we can find the work done. So we know the force, we just calculate the force value, and the distance is given. Pushing distance is 1.9 meter. Therefore we can find the work done, which is W equals force times displacement. Now force is 58 Newton, displacement is 1.9 meters. Therefore the answer is 110 Newton meters, or we can write it as joules. Next, in part B, we are asked to find the distance D if the work done is 140 joules. Therefore we can use the same equation, W equals Ft, and we have to find distance. Therefore D is equal to W over F, work done over force, and D is equal to work done is 140 joules. In this case it is given in the problem, and force is 58 Newton, and therefore the answer is 2.4 meters. So now you know how to manipulate the equation W equals Fd. Now what if the force is not in the direction of displacement and it is an angle to the displacement? So in this figure we see a person pulling a suitcase on a level surface with a strap that makes an angle theta with the horizontal. So in this case force is at an angle to the direction of motion. It is not in the same direction. So therefore, now how do we calculate the work in these type of cases? So well, instead of force times distance, now we can say that the work is the component of force in the direction of displacement times the magnitude of the displacement. So the component of force in the direction of displacement is, in this case, F, cos theta. Therefore, work done is F cos theta times D, or we can simply write it as FD cos theta. Now, if the force is in the direction of motion, then this angle should be 0. Therefore, if we use this equation, cosine 0 is 1. Therefore, the work done is FD. It is as we expected, because if the force and the displacement is in the same direction, then the work done is force times displacement. And now in the case where theta equals 90 degree, that means the force and the displacement are perpendicular. In that case, cos 90 is 0. Therefore, work done is 0. So, if the force and the displacement are perpendicular, the work done should be 0. Now, the displacement of the suitcase in this figure is equivalent to a displacement of magnitude d cos theta in the direction of force F, and plus the displacement of magnitude d sin theta perpendicular to the force. But as we learned in the previous slide, only the displacement parallel to the suitcase results in non-zero work. Therefore, the total work done is FD cos theta, as we expected. So, for work done, we can write as F cos theta times D, or F times D cos theta. Either case is correct. So, the final value is FD cosine theta. Theta is the angle between the force and the displacement. Now, let's see an example using that formula. In a GES system, an enclosed lifeboat on a large ship deployed by letting it slide down a ramp and then continuing free fall to the water below. Now, suppose the mass of the lifeboat 4,970 kg slides a distance d 5 meters on the ramp, dropping to a vertical height of 2.50 meters, that is h. We are to find the work done by gravity on the boat. Now, from our sketch, we see that the force of gravity and the displacement are at an angle theta relative to one another when placed tail to tail, and that theta is also the angle that the ramp make with the vertical, this angle. Now, by definition, we know that work is force times d cos theta, and in this case, force is simply the force due to the gravity, which is equal to mg, and d is given, which is 5 meters, and the angle theta is the angle between the force and the displacement. But the theta value is not given, but we can calculate the theta because we know the h and we know the displacement d. Therefore, cosine theta is simply h over d. So, we can find the angle theta from this sketch. Now, let's solve the problem. So, these are the known parameters: the mass of the lifeboat, sliding distance, and the vertical height. And we need to find the work done by gravity, which is mg. Now, first we need to find the force which is due to gravity. And to find the force, we need the force component in the direction of displacement, which is F cosine theta, and in this case F is simply mg. So, we know that force is equal to mg, and we found that cos theta is equal to h over d. So, therefore, we can write F cos theta is equal to, F is simply mg and cos theta is h over d. So, we can substitute the values to find F cos theta. So, F cos theta is, mass is 4970 kilogram. Gravity is 9.81 meters per second square and h is 2.50 meters. D is 5.00 meters. Therefore, F cos theta is equal to 24,400 Newton. Now we can find the work done because we know the component of force in the direction of displacement, which is F cos theta. Therefore, work done is W, which is equal to FD cos theta, or we can write it as F cos theta times D. So we found F cos theta value, which is 24,400 newtons, and D is given, which is 5 meters. Therefore, the work done is 122,000 joules. Now we can find the same value with another method. So we can first find the work done in symbolic form. Now we know that work done is F cos theta times D, and F cos theta we can use F is mg, cos theta is h over D times distance. Therefore, it is simply mgh. So if we solve for this equation, we can get exactly the same value. So in this case, the work is simply mgh, exactly same as if the lifeboat had fallen straight down through the height h, which is mgh. Now work done can be any value, positive, negative or 0, depending on the angle between the force and the displacement. So if the force has a component in the direction of motion, that is if theta is between minus 90 degree and plus 90 degree, then we say that work is positive. And if the force has no component in the direction of motion, that is if theta is 90 degree or negative 90 degree, then the work should be 0 because force is perpendicular to distance. So the work is 0. And if the force has component in the opposite direction of motion, it can happen. Then in that case, the work is negative. So work can be negative, 0 or positive. And when more than one forces act on an object, how do we find the work? Then the total work is the sum of the work done by each force separately. Therefore, if force F1 does work W1 and if force F2 does work W2 and so on, we can find the total work done by adding all those values together, which is sigma W, sigma work done. And equivalently, the total work done can be calculated by first performing the vector sum of all the forces, which is F total, acting on an object to obtain the total force, and then using our basic definition of work F cos theta times D. So it is simply F total times D cos theta. And in this case, theta is the angle between the total force vector and the displacement vector. Let's see an example before moving to the next section. A car of mass m coasted down a hill inclined at an angle 5. The angle is 5 below the horizontal. The car acted by 3 forces: the normal force, which is always perpendicular to the surface, and the force due to air resistance, F air, which is always opposite in the direction of motion, and the force of gravity mg, which is in the vertical direction, vertically downward. And we are asked to find the total work done on the car as it travels a distance d along the road. Now this angle 5 is the angle the slope makes with the horizontal, this angle, and also it is the angle between the gravity mg and the downward normal direction as in this figure. Therefore, we can write the angle between mg and the displacement, this angle is 90 minus 5, and the angle between the normal force and distance is simply 90 degree. Therefore, normal force shouldn't have any contribution to the work done. And the next force is the force due to air resistance, which is F air, and it is at the angle of 180 degree. So it should have a component that is due to the work. Now there are three forces acting on the car as we discussed, and for each force we can calculate the work using W equals Fd cos theta. And first, the work done by the normal force. As we discussed earlier, the normal force and the distance is perpendicular, which is the angle is 90 degree, therefore it is 0. There is no contribution from the normal force. And then the work done by the air resistant, which is completely opposite to the direction of motion. The angle is 180 degree, which is cos 180 is minus 1, therefore it is a negative value. The force times displacement, but it is a negative value. The next one is the work done by gravity, which is Fmg times d, and angle in here is cosine 90 minus 5. 90 minus 5 means sine 5, and force due to gravity Fmg is simply mg, therefore it is mg d sine 5. Now we can find the total work done by adding all these work values. So we have to add the work done by normal force, work done by force air resistance, and work done by gravity, and we are getting this value for work done. Now this is the end of the first section of chapter 7. So far we learned the work done by a force is W, which is Fd cosine theta. Now here F is the force and D is distance, and theta is the angle between the force and the displacement. And then the work is positive when the force and displacement are in the same direction, and if it is 0 if the force and distance is perpendicular, and it is negative if it is in opposite direction. So it can be positive, negative or 0.